So the last major topic we need to cover for the semester is the concept of vector fields. And we're going to talk about vector analysis. So a vector field is something that I'm sure many of you are familiar with. So suppose you have a region in 2D or 3D space that essentially is occupied by this, say, moving fluid. Okay, fluid is a very rough term here. It could be air or water or any particles that are moving. And so the idea here is this fluid is made up of a series of particles, and those particles are going to be moving in a particular direction. So therefore we could associate a vector with each one of those particles. The set of all those vectors that's associated with every single particle is essentially what we're going to call a vector field. So if you can think of a couple of examples, let's say like a river and water flowing through the river, which would be the example I have here. And so each particle of water has a little vector associated with it. And you see kind of a collection of a whole bunch of these put together here. And the bigger the vector, the faster the particle of water would be moving. The smaller the magnitude of the vector, the slower the water is moving. You kind of see it coming up to this rock here and how it would have to veer away, and then how that would change, one, the direction, and two, the velocity of that water. Well, the collection of all these vectors together with all the points that are associated with each vector is a vector field. You could also think about this as wind shear off, say, a car, maybe a gravitational field, electric, magnetic field, etc. These are all vector fields. So we'll formally define a vector field really as a function. And so here's another new function that we're going to talk about. You know, up to this point in mathematics, you've talked about real functions of a single variable, real functions of multivariables. We've talked about vector valued functions, and now we're talking about vector fields. It's really a new type of function. And so it could be a two-dimensional vector field or a three-dimensional vector field. We will deal with both. And it's whether or not you associate a two-dimensional point or a three-dimensional point with a particular vector. And that vector is either going to be a two-dimensional vector or a three-dimensional vector. And so the notation will look something like this. This would be a 2D vector field. So we have a point that we're going to plug into the vector field, and that's going to then be associated with a particular vector itself. That would be 2D, this would be 3D. We have a 3D point that we're going to plug into the vector field, and we're going to associate it with a particular vector here. So if you think about this in our function notation, where we have one set going to another, the vector field function would take a point, say x and y, and associate it with a vector, say f1 of x and y, comma f2 of x and y, because the components of this vector field could be different for different points, so they're based off of these two functions themselves. These functions are called the component functions in the vector field. Okay, so what this basically does is it kind of mixes together multivariable functions and vector valued functions into one thing called a vector field. So here's a quick example. Say here we had a vector field defined by these two functions for the components. I is the first component, j is the second component. And so this is a two-dimensional vector field because you're going to plug in a 2D point and you're going to get a 2D vector. And so what we want to do is we want to figure out what vector is associated with the point 0, negative 1. So if I start at 0, negative 1, what vector does that match up with? Okay? So if I have this particular point, 0, negative 1, which is right here, what vector am I going to attach to that point? And so you just basically plug the point into the vector valued function, 0 for x, negative 1 for y. This tells you what the component should look like based off of that, so you plug it in. And you end up with negative 2 for the I, and cosine of 0 is 1 for the j, so there's your vector. So the vector negative 2, 1, either an ij notation, or in this case bracket notation, is the vector that's associated with the point 0, negative 1. So vector fields take points and associate vectors with points, and the collection of all those points and all those vectors creates the vector field. Here are a couple of pictures of some random vector fields. This maybe could represent, say, an explosion. This obviously would be representative of a tire spinning around. This could be a gravitational vector field. These first two are two-dimensional vector fields. This one's a three-dimensional vector field. Notice we don't use every single point, right? I just pick a selection of points and look at their particular vectors. But the domain for this vector field could be all points in the xy plane, but I can't look at what every single point's vector is, because then this would just be solid all the way through. I mean, you would have all your points collected together and all their vectors. You wouldn't see anything. So we just take a collection of some real specific points and their associated vectors, and we take a look at this. And just by staring at something like this example here, you could see that the closer I am to the center of the tire, the shorter the magnitude of the associated vector, which means the slower the speed. You know, if you think about the magnitude of this vector as, say, the velocity or the speed, then I can see that I'm going faster if I'm on the edge of the tire, and the speed of rotation would be slower if I'm on the inside. You know, something like this. The gravitational force in here is stronger than on the outside here, if that's a gravitational vector field, etc. So, you know, these could all be different things, but these are just some examples of vector fields. There's something called a unit vector field. None of these examples are actually unit vector fields. A unit vector field, the magnitude of every vector in the field is a magnitude 1. These all have different magnitudes, so none of these are unit vector fields. But if your vector field, every vector in the vector field has the same magnitude and it's 1, it's a unit vector field. A radial vector field is a vector field that depends on a distance r from some point in the origin. So every vector, depending on how far it is from the origin, its vector is associated with that and dependent on that. These would all look like possibly radial vector fields. They all deal with, you know, a certain distance from the origin is going to affect the vector itself. So they could all be radial vector fields. One specific type of vector field we're going to deal with a lot in this unit is a gradient vector field. We've actually talked about the gradient already, and we talked about how, you know, if we had, say, a mountain here and we were standing on the side of the mountain, that the gradient vector, right, the gradient vector will point us straight up the mountain, right, to this place where the slope is the biggest. Well, if I take every point on this surface, which is the mountain, and I look at the gradient at every single point, the collection of all those is a gradient vector field. And so we've actually already talked about this previously without even talking about vector fields themselves. Another name for a gradient vector field is called a conservative vector field. Okay, and so the idea here is, if we look at the gradient of some function f, okay, and we look at the vector field based off of all those gradients, which would be just the partial derivatives with respect to x, y, and z as the components, this would make up the field. So we would call that a conservative vector field. The function that we took the derivative of to get these components, this function f, we're going to call the potential function of that gradient, of the gradient vector field, of the conservative vector field. Now, some vector fields don't come about this way, right? Vector fields can come about from all different things. But if a vector field does come about through this process of creating the vector field, where the components of the vector field are the partial derivatives of some function, again, that vector field is called a conservative or gradient vector field, and the function that you took the derivative of is called the potential function. So if I had this function and I wanted to find the gradient vector field for this function, I would need to find my partial derivatives with respect to x, y, and z, and then I would have to make a vector field from those partial derivatives. Okay, so what's the partial derivative with respect to x? Well, in this case, you would just get y. The partial derivative with respect to y, I would get x plus z squared. And the partial derivative with respect to z would be 2yz. And so the vector field is going to be a 3D vector field. So x, y, z would be, I'm going to run out of room here, y is the first component, x plus z squared is the second component, and 2yz is the third component of that vector field. And I plug any point in here, and I could say, I don't know, point 1, 0, 0. I could figure out what vector is going to be associated with that. In this case, I would get 0, 1, 0. Right? But this vector field is a conservative vector field, and this would be the potential function for that vector field. This is going to be a pretty important concept as we move through this concept of vector fields, because this will be a vector field that is fairly easy for us to work with using a lot of the things we've learned along the way in the semester. So, let's say we have a vector field sitting in front of us. How would we know if that vector field is a conservative vector field? Therefore, how would we know that the components of the vector field came from partial derivatives of some function which we call a potential function? Or maybe it's just a random vector field that came from some other place. Okay? Well, we can determine this by using this cross partials property for conservative vector fields. So it says, all right, if we have a vector field, and this works for 2D or 3D vector fields, but I have it here as for 3D. So let's say we have this 3D vector field. So you have a three-dimensional point and three-component vector. So let's say this vector field, we're trying to determine if it's conservative. What this says is we can determine if this vector field is conservative by looking at these three cross-partial equations. Okay? If all three of these things hold, then we have a conservative vector field. So what it says is that the partial of f1 with respect to y equals the partial of f2 with respect to x. The partial of f2 with respect to z equals the partial of f3 with respect to y. And the partial of f3 with respect to x equals the partial of f1 with respect to z. Easy way to remember this is I do this, f1, f2, f3, x, y, z. So that's the first cross partial. F1 with respect to y has to equal F2 with respect to x. Here's the second cross partial. F2 with respect to z equals F3 with respect to y. And then the third one is F1 with respect to z equals F3 with respect to x. And if all three of these hold, then what we have is a conservative vector field. We have a vector field that came from a potential function. All right. If it's only two-dimensional, then there is no z, and there is no f3, and therefore this isn't here, this isn't here, this isn't here, this isn't here. Anything with an f3 or a z is gone, then this is the only piece that you need to know. So as long as this first equality holds, then it's conservative. The reason why this works has to do with the concept of the mixed partial derivatives concept. One thing we talked about is that the mixed partials, fxy should equal fyx, as long as our function and our derivatives are continuous. Well, what we're saying here is that if f1 is the derivative with respect to x, and f2 is the derivative with respect to y, and f3 is the derivative with respect to z, by finding the partial of f1 with respect to y, you're basically finding xy. And if you're doing the partial of f2 with respect to x, you're basically finding fyx. And you're saying, okay, well, basically, I should use lowercase f for all these. Okay, that's what we're talking about, the function itself, the potential function. We're basically saying, well, if this is true, then that means this originally was the derivative with respect to x and the derivative with respect to y, if these mixed partials are equal to each other. So it's basically kind of taking that one step further. And continually through these other mixed partials, it's the same idea. So, cross partial, you're basically finding all the mixed partials and seeing that fxy equals fyx, fyz equals fzy, etc. All right, so here's an example. Let's get rid of all this. This is a vector field right here. It's a constant vector field because all the components of the vector field are constants. Is it conservative? Okay. Show that it is conservative. Well, here's F1, here's F2, and here is F3. So does the partial of F1 with respect to y equal the partial of F2 with respect to x? Well, since they're all constants, these partials are going to all be 0, right? No matter what variable we're talking about, the derivative with respect to any variable of any one of these three things is going to be 0. So those next partials will equal each other. Partial of F2 with respect to z should equal the partial of F3 with respect to y, again, both being 0. And the partial of F3 with respect to x should equal the partial of F1 with respect to z, again, both should be 0. So is it conservative? Yeah, it's conservative. What can you say about any constant vector field? Well, they're all going to be conservative, right? Because the same thing's going to happen every single time. If all my components are constants, no matter what derivative I'm doing of any one of the components with respect to any variable, everything's going to be 0. Okay? They're not always that easy. How about this one? Is this one conservative? Being it's a 2D vector field, we only have F1 and F2. So we only have to check that the partial of F1 with respect to y equals the partial of F2 with respect to x. If that holds, it's conservative. Well, what's the partial of F1 with respect to y? 15y squared. How about the partial of F2 with respect to x? That would just be 15y. They are not equal to each other, so this one is not conservative. Okay? Well, what does that mean? It means there is no potential function. There is no function of x and y that I took the derivative of to get this component and this component. That's all. Where did it come from? Who knows? But it didn't come through the concept of the gradient and derivatives to get this vector field. How about this vector field? Is this one conservative? Well, this is a 3D vector field. There's F1, there's F2, and there is F3. So I need to do my 3 mixed partials. So the partial of F1 with respect to y has to equal the partial of F2 with respect to x. All right, so let's see if that holds first. E to the x cosine y with respect to y. X is a constant, so this is going to be minus e to the x sine y. And that has to equal F2 with respect to x. So this with respect to x is the variable, y is the constant, would just be minus e to the x sine y. Derivative of e to the x is e to the x. Everything else stays the same. So does that hold? Yep. All right, let's go to the next one. Partial of F2 with respect to z has to equal the partial of F3 with respect to y. All right, well, F2 with respect to z, there are no z's in F2, so that's just one big constant and 0. F3 with respect to y, again, there's no y's in F3, so that's 0. That one holds. All right, and finally, partial of F1 with respect to z has to equal the partial of F3 with respect to x. Well, there's no z's in F1, so that's a constant, and therefore 0. And there's no x's in F3, so that's a constant, and that's 0. So that holds. So is this conservative? Yeah. This is conservative. Okay? All right, now once we determine it's conservative, so what function? What is the potential function? What function of x, y, and z did I take the derivative of with respect to x to get this, with respect to y to get this, and with respect to z to get this, did I use? What is the potential function? There is one, since it's conservative. What is the potential function? That's the next question. Okay, so to find this potential function, we first have to know that it exists. So we want to know if we have a conservative vector field to start with. All right, so what we're going to do is we're going to look at a vector field on what we call a simply connected domain. Basically, it's a domain that has no holes. Remember, the domain for these vector fields are either a set of 2D points in the xy plane or a set of 3D points in the xyz space, right? And so the idea is, let's just say it's 2D. All these points are in the domain. We kind of look at them as an area, and the area is all the points filled in, okay? So all those points that make up this space are in my domain. I'm not, say, missing this point or missing this point or missing this point. So a simply connected domain is a domain with no holes in it, okay? So if f satisfies the cross partials, meaning that it's conservative, then we're going to say it has a potential function, okay, over that simply connected domain. Now, how do we find it? Well, remember that what we're saying is that when we look at a vector field, okay, we have a vector field. Let's say we have a 3D vector field. Oops, that should be a z. And that vector field is comprised of three functions, f1, f2, and f3. What we're saying is that this is the partial of some function with respect to x. This is the partial of that exact same function with respect to y. And this is the partial of that exact same function with respect to z. That's what we're saying. If this is conservative and we're trying to find a potential function, we're trying to find the function such that the derivative of it with respect to x is equal to this first component. The derivative of that exact same function with respect to y is this component, and same thing for the third. And we're trying to go back and find the function itself. Well, if we took the derivative to get here, here, and here, then we should probably integrate f1 with respect to x, which is the variable we differentiated to get there. We should integrate f2 with respect to y, and then continue that to integral of f3 with respect to z, and they should all equal each other because they should all go back to that function we're trying to build. And so that's how we do it. If we got to this function through differentiation, if we got through this vector field through differentiation, we should go back to the potential function through integration. So here's an example. Determine first if this vector field is conservative, and if it is, go find the potential function. Well, it's a 2D vector field, so I only have to see, does the partial, this is f1 and this is f2, does the partial of f1 with respect to y equal the partial of f2 with respect to x? Well, f1 with respect to y would be 2xy. f2 with respect to x would be 2xy. They are equal to each other, so this is conservative. Therefore, there is a potential function, and I can find the potential function simply by integrating. I should integrate xy squared with respect to x because I got this piece by differentiating with respect to x. And I should also integrate f2 with respect to y. But remember, they should equal each other because they're both going to go back to that function f. This is going to give me that function f. This is going to give me that function f. So they should equal each other. And that's really the key to getting this to work. So if we did this integral with respect to x, y is treated like a constant. And therefore I would get x squared over 2 times y squared. But this is an indefinite integral, so I should have a plus c. However, c isn't necessarily a constant, but it's a function of everything I held constant. Well, I held y constant, so really it could be some function of y. Think about it. If I took the derivative of this with respect to x, this piece would give me this, and this piece would be 0. Because it only has y's in it, and y is treated like a constant. It could also just be a constant itself. It could just be 2, but it could also have y's in it. So at best, the biggest it could be is this function of y. That's my constant of integration for the first integral. Now, I do the next one with respect to y. Well, that's going to be x squared, y squared over 2, plus the c there. But this is a different c. This c is a constant of integration for this integral, but I treated x like a constant, so this c could be some function of x. Okay, so now that's the c for this integral. That's the c for this integral. But remember, both of these have to equal each other, right? So if this has to equal this, well, we clearly see these two pieces are equal, so therefore these two pieces have to be equal. Well, the only way that g of y could equal h of x, a function that only has y's in it, equals a function that only has x's in it, the only way they could equal each other is if both of them are simply just a constant themselves. They don't have any x's or y's in them. And so the potential function, f of xy, at best is going to be x squared, y squared over 2 plus some constant c, which we won't be able to figure out what that c is. Okay, here's another one. So let's determine if this three-dimensional vector field is conservative. And if it is, let's find the potential function. So first, does it satisfy the cross partials? So f1 with respect to y has to equal f2 with respect to x partials, right? And so f1, f2, y would be z, f2 with respect to x would be y, and so it doesn't hold. First cross partial doesn't hold. So if the first cross partial doesn't hold, then it's not conservative. Conservative. And therefore there is no potential function. Done. If that's the question, that's it. It's done. All right, so this one, let's find the potential function for this vector field. So it's basically already telling you that this is conservative. So we don't have to check that by asking you to find the potential function. It's kind of insinuating that. There's f1, there's f2, and there's f3. It chose to write this in IJK format instead of the bracket notation, but it doesn't matter. These are all legitimate ways of writing vectors. And so what we want to do is the integral of f1, which is 2x cosine y minus 2z cubed. We want to do that with respect to x. And that should be equal to the integral of f2, which is 3 plus 2y e to the z minus x squared sine y with respect to y. And that should equal the third component with respect to z. So the integral of y squared e to the z minus 6xz squared, again with respect to z. And they should all equal each other. They should all be equaling this potential function that we're trying to build. Okay? So let's look at each one of these integrals. So with respect to x, y, and z are constants. So this would be x squared cosine y minus 2xz cubed plus our constant of integration. Well, our constant of integration could have both y's and z's in it because both of those were treated like constants. So g of yz. And I'm going to run out of room, so I'm going to say equals. We'll do this next one with respect to y. So with respect to y, I should get 3y plus y squared e to the z minus, with respect to y here, I'm going to get actually plus x squared cosine y. Plus my constant of integration, that could be a function of both x and z, because both of those are treated like constants. All right, and that should equal, and I'm going to put it down here, the integral of this with respect to z. So what are we going to do? We're going to do the integral of y squared e to the z with respect to z, so it'll just be y squared e to the z minus 6xz squared, so that would be 2xz cubed plus some function of, let's say, k of x and y. Now all these have to equal each other, and so we need to put all of these pieces together to build the potential function that we were looking for. And so a lot of these pieces are similar pieces, so let's look at the first two. I have an x squared cosine y and an x squared cosine y, so clearly they equal each other. And that's about it. So that means the remaining pieces, this whole thing, and this plus this whole thing, they have to equal each other. Okay, well, how's that going to work? Well, I have something that only has x's and z's in it here. That could be equal to this piece that's only supposed to have x's and z's in it. And I have this piece here that only has y's and z's in it, and that could be equal to this piece that only has y's and z's in it. So we could use that. And so if I said that, then that means my function that I'm looking to build would just be x squared cosine y minus 2xz cubed plus 3y plus y squared e to the z plus potentially maybe another constant somewhere down the road. Okay, that kind of came into play with all of these. If I look at that with this one here, is that possible that this could also equal this function, or matching it up with this one? Well, I have the y squared e to the z. I have a 2xz cubed. And then what do I have left? Well, I have this piece left. I have this piece left and my constant. Well, that would have to be equal to the remaining piece here that can only have x's and y's in it. Well, guess what? These two pieces only have x's and y's in it. So if I match it up with all three of these, this is what the potential function should be. And if I were to take the derivative of this thing with respect to x, I would get that. If I took the derivative of it with respect to y, okay, sorry, I wouldn't get that. I would get that. If I took the derivative with respect to z, or to y, I would get that. And the derivative with respect to z, I would get that. So this is my potential function. And so that's the key of setting all these equal to each other and matching up the remaining pieces to see which pieces have to equal what with these random functions that we have here at the end.